Hey everyone, and welcome to This Explainer. Today, we are diving into something pretty incredible, the fascinating and, honestly, mostly unseen world of railway maintenance. It's totally the unsung hero of our daily commutes. Think of it as the invisible engine that powers the vast transit networks we rely on every single day. So, we're going to pull back the curtain and look at the intense engineering that keeps these massive systems running so smoothly.
Have you ever actually stopped to wonder, maybe while you're waiting on a platform or just staring out a train window, how literally millions of trains manage to run every single day without completely breaking down? We kind of just expect the train to be there, right? To be safe and to be on time, but achieving that reality takes an immense, highly coordinated effort behind the scenes. Okay, let's dive right into this. Because a functioning railway, it's definitely not magic. It is an absolute triumph of continuous, rigorous upkeep. Basically, maintenance is the systematic process that keeps a railway system dependable long after it's been designed, installed, and tested. Its number one goal is to ensure the railway delivers a safe and efficient service throughout its entire operational life. It's the very thing that transforms a static pile of metal and concrete into a living, breathing, reliable transit network. So here's how we're going to break this down today. We'll start with the unsung hero of maintenance, move right into system dependability, tackle reliability and availability, explore maintainability, and finally, wrap up with safety and security. All right, part one, the unsung hero. Let's look at the critical role of maintenance. When you look at the tracks, visual systems, like glowing green signals or track switches, well, they're really just the tip of the iceberg. Behind every single signal lies a massive, systematic engineering effort. Track circuits, signal lamps, point machines, they all require continuous, extremely precise upkeep just to function in extreme weather, not to mention under the immense physical stress of heavy trains passing over them. Delivering a safe service for decades requires constant, unwavering vigilance. Moving right along to part two, system dependability, or what I like to call the master blueprint. So what exactly is dependability? In engineering speak, it's a collective term for all the qualities that allow a system to perform exactly the way we need it to. And it's fundamentally built on four pillars, known by the acronym RAMS. That stands for reliability, availability, maintainability, and safety. And layered over all of that, security. It acts as a vital, cross-cutting concern touching every single one of those four elements. Without dependability, you simply do not have a functional railway. Let's move to and see how this builds with part three, reliability and availability, our first two pillars. First up, we have reliability. What this basically boils down to is probability. It's the probability that a system or a specific component is going to do its job exactly when it's supposed to. It answers one very simple but incredibly critical question. Will it work exactly when it is needed? Like, if a train runs over a track circuit, will that circuit reliably detect the train every single time? Now, to actually measure that reliability, engineers use a specific metric. It's called mean time between failures, or MTBF. The math is actually pretty straightforward. You just take the total length of time a group of items is in service and divide it by the number of failures during that time. So imagine you've got 120 track sensors out there, and they have 50 failures over a year. Your MTBF is 2.4 years. It gives engineers a clear mathematical baseline for how long a part will live. But, abstract math always meets a very gritty reality out there on the tracks. Things go wrong. We're talking about poor design, pesky software bugs, insane weather conditions, flooded or contaminated track beds messing with electrical signals, and even electromagnetic interference coming from the trains themselves. A highly reliable system has to be designed to either tank through these harsh elements or self-diagnose before a total meltdown occurs. Okay, so how does that differ from availability? Well, availability is the proportion of time that the system is actually in a state to do its job. Think of it as continuity of service. It's asking the question, for how much of the time is this system actually usable for running trains? We figure this out with a pretty simple comparison, uptime versus downtime. The formula is literally just uptime divided by the total of uptime plus downtime. And keep in mind, downtime isn't just surprise failures. It includes planned maintenance that takes the track out of service, too. To boost this number, engineers love using redundancy. That means duplicating critical parts, so if one fails, a backup takes over instantly. That keeps the whole system highly available, even if individual components still break at the same rate. Which brings us to part four, maintainability.
the third pillar. So, maintainability is all about ease, specifically the ease with which a component can be kept in working order or repaired. Because look, a system could be incredibly reliable, running flawlessly for 10 years, but if it takes dismantling half the track just to change a single sensor when it finally does break, yeah, that's terrible maintainability. And this brilliantly illustrates why smart design choices are absolute game changers. High maintainability means having components that are easy to access. It means using modular designs, literally like building blocks, so a broken part can be swapped out in minutes. It means having effective diagnostic tools to pinpoint faults immediately and remote condition monitoring that literally alerts engineers to wear and tear before a failure even happens. All of this drastically slashes repair times. All right, on to part 5, safety and security. These are the absolute ultimate priorities. Let's talk safety. In the engineering world, this means freedom from unacceptable risk of harm, whether that's to people, the equipment, or the environment. On a railway, absolutely everything must be designed to fail safe. That means if a component breaks, the whole system automatically defaults to its safest possible state. Usually that means turning all the signals red and stopping the trains dead in their tracks. It degrades gracefully rather than causing a massive catastrophe. And we really have to look at both sides of the safety coin here. On one side, there's system safety. This is all about the machinery, protecting train movements, ensuring interlockings actually work, preventing collisions and derailments. But on the other side, staff safety. We absolutely have to protect the technicians, the signalers, and the operators working out there on the tracks. A truly safe system never exposes its maintenance crews to unnecessary danger. When you look at system safety in action, it's fascinating to see how trains actually stay apart. Modern engineering calculates exact braking distances based on how fast and how heavy a train is. Now, in older fixed block systems, a train basically owns a static section of physical track. But in advanced moving block systems, an invisible digital safe zone moves continuously right along with the train. This complex, real-time spatial math is what enforces system safety and makes sure trains never collide. No, the final piece of this whole puzzle is security, and we're talking about protection against malicious external actions. That could be cyber attacks, folks stealing copper cables, or just physical vandalism. And as railways become more and more digitized and connected over networks, cybersecurity is literally non-negotiable. We have to prevent unauthorized access from disrupting operations, or worst case scenario, causing actual injuries. So the crucial point is how this all connects. Part 6, the complete picture. Bringing RAMS all together. Let's pull all of this together into one neat package. We've got reliability, which is your probability of function, tracked by MTBF. Then availability, which focuses on your pure uptime. You have maintainability, focusing on the ease of repair using modular access. Safety, ensuring complete freedom from harm via fail-safe designs. And security, acting as the shield protecting the whole network from malice. Together, they create the dependability that makes modern transit possible. So I'm going to leave you with this one thought. The next time you step onto a train, as you grab a seat and settle in for the ride, just ask yourself, what invisible systems are calculating the safety of your commute in that exact second? From the modular parts under the floorboards to those invisible moving blocks of digital space keeping you safe from the train ahead, it's a total marvel of continuous engineering. Thanks so much for joining me for this explainer, and keep learning.